Okay, we're going to look at two different types of materials. Those are insulators and conductors. Um, Now, in conductors, electrons move freely in response to other charges. You're probably very familiar with conductors. Um, Good electrical conductors are often good thermal conductors. So, for example, metals, like copper, for example, is an excellent electrical conductor, and that's why we use it in our houses. It's also a very good thermal conductor, which is why we use it for pots and pans and what have you. So metals such as copper. Now insulators, on the other hand, the electrons do not move freely. So they're tightly bound to the nuclei. And similarly to the conductors, if it's a good electrical, or if it's a bad electric, if it's an electrical insulator, excuse me, then it's probably also a good thermal insulator. So, rubber, wood, those sorts of things. Fiberglass. Yeah. Now, let's look at examples of discharging. Actually, also semiconductors. We're not going to get into this, but I'll just sort of list it here. Semiconductors are a material that becomes a perfect conductor under particular conditions. When we get into circuits, we'll talk a little bit about a semiconductor device. In a conductor, if one area of a conductor becomes charged, then the charge is going to evenly distribute itself across the entire surface. This is an important idea when we're looking at how charges are transferred on conductors. Uh, just sort of to keep this in mind, that when you have a distribution of charge, it's going to be evenly distributed across the conductor. That's not true for insulators now. You can have an excess of charge on an insulator, but that charge is not going to move around. So say, for example, let's say that you have a conducting sphere here. This is a conducting sphere made out of metal or whatever, and you deposit some electrons. Now these electrons, because they're like charges, are going to be repelled from one another, and because of those repulsive forces, we're going to get a distribution of charges where they're evenly spaced all over the sphere. All right, so they're going to find this equilibrium position where they're evenly spaced, and it's because of those repulsive charges. However, when an insulator becomes charged, the charge stays in place. So if I place these on an insulator, then they're not going to move at all, because an insulator, the electrons don't readily move around. So they're going to stay exactly where you put them. Let's say, for example, I want to charge something by conduction. So I have two objects. I have a charged conductor, or I have a metal rod, for example, that has electrons on it, and then I have a neutral conductor, or a metal ball that has equal numbers of positive and negative charges. All right, so I would draw this more particularly. If I bring this charged conductor up here, before my neutral conductor is going to have equal numbers of positive and negative charges, and they're going to be situated sort of randomly on the object. But when I bring a charged conductor up next to the neutral conductor, we're going to get a charge distribution that looks like this. I'll have positive charges over here and negative charges over here. Now keep in mind that the positive charges don't actually move So really what's happening here is these negative charges here come close to this neutral conductor, and all the negative electrons are going to be pushed over to this side, leaving a positive excess on this side. Now, if I touch the charged conductor to the neutral conductor, then these electrons are going to go onto the conducting sphere. Because I've had this excess of positive charges over here, and then I'll still have the negative charges that were over there. Now what that's going to cause is a net excess of negative charge. So now I'm going to have more negative charges than positive charges. And that's charging by conduction. All right, I can charge a conductor by touching it with another charged conductor. Charging by conduction. Conduction generally means to touch something. We can also charge by induction. This is a little bit different. Now, when I have charging by conduction, it requires contact between the two objects. But charging by induction, there's no contact between the objects. So let's say I have a neutrally charged conductor. Right? Notice that I have equal number of positive and negative charges. And then I bring a charged bar, conductor, insulator, otherwise. Let's say it's negatively charged insulator. It doesn't really matter. And I bring it up here. And then I get a distribution of charges that's going to look like this. I'm just going to write plus and minuses here. I get a distribution of charges. The negative charges all go off to the edge of the sphere. And it looks like that. And then I have these charges here, charges here, charges here. I attach a ground. This is just a wire that provides a place for the charges to go. And these charges will go down and go away from the sphere. This is called a ground. We'll see this again when we get into household circuits. But it just provides a place for charges to go. It goes onto the earth, and the earth is basically a sink for all charges to go into. And so those negative charges leave the sphere and go into the ground. And then that leaves, when everything is taken away, it leaves a positively charged sphere. Now that's called charge by induction, charge by induction. And it requires no contact between the two charged objects. All right, I have a little demo I want to show you. This is from MIT. It's a physics demo. As you watch this, there's a description down below. He's going to be dealing with some tinsel like you used to put on your Christmas tree. I don't think people do this anymore, but the silver tinsel that you put on your Christmas tree. And what happens when he brings that close to charged objects. And then also he uses a mylar balloon, which is a conducting balloon. So remember, both tinsel and the balloon are both conductors. So as you're watching this, remember the tinsel is a conductor. The balloon is also a conductor. And he uses a plexiglass rod, and when he rubs it with rabbit fur, plexiglass, that's the clear rod. When he rubs it with rabbit fur, it becomes positively charged because the rabbit fur takes away electrons from the plexiglass rod. And then he also uses a rubber rod. This is the black rod that he uses. And the rubber rod becomes negatively charged when he rubs it with the rabbit fur, because the rabbit fur deposits negative charges onto the rubber rod. All right, so I want you to watch this video. Oh, by the way, if you wish to do this, you can, most people don't have plexiglass or rubber rods, but you can also use a length of PVC pipe and maybe a wool sock. And the PVC pipe and the wool sock, if I remember correctly, it sort of depends upon the molecules, but if I remember correctly, it becomes negatively charged. And then you can do all sorts of cool charge demonstrations like this. So let's go and watch the video. It's right here.